Let's talk about the structure and properties of ethers. So we know water looks like this. It has a bent conformation or configuration, and it has an angle of about 105 degrees between these two. There are lone pairs on oxygen, and that allows it to strongly hydrogen bond with other water molecules. So water has a very high boiling point, 100 degrees Celsius. Now alcohols, we've learned, also have an OH bond in the molecule. So that allows them to hydrogen bond to other water molecules, and it makes molecules that have 4 carbons or fewer that have an alcohol or a hydroxyl group water soluble. Okay? Because methanol has an hydrogen here, an OH, it has lone pairs, it can hydrogen bond, it's polar, and it has a reasonably high boiling point. Methanol boils at, well, I don't have the number here in front of me, okay? 60 something degrees, okay? So this is going to have a reasonably high boiling point. Now ethers, they do not have an OH bond, so they cannot hydrogen bond to other molecules of dimethyl ether. In fact, dimethyl ether is a gas, and it is still bent, okay? The bond angle here is 112 degrees. Why is this 105 and this 112? Well, the methyl groups are kind of sterically large, so they push away each other, okay? So that's why the bond angle is a little bit more. Now this molecule does have a lone pair. It can hydrogen bond to water, but not enough that ethers are going to be water soluble. This has a very low boiling point because it doesn't have an OH bond. It cannot perform hydrogen bonding, okay? It is slightly polar, but that's all. It's going to be a very low boiling substances, okay? So ethers are very low boiling point, okay? Of course, if an ether has more carbons due to like a butyl group or something like that, maybe a propyl group on this side, because of the increased surface area, that's going to have greater London dispersion forces, and therefore it's going to be maybe a liquid at room temperature. Okay, so that's the basics of the properties of ethers. Okay. Now, crown ethers is briefly mentioned in your textbook. The reason for using crown ethers is to increase the nucleophilicity of the anion in solution and to make that react in something that's nonpolar, for example, okay? So if you wanted to react, so 14.4 crown ethers. Okay, so if we had something like this, okay, and we wanted to treat this with potassium fluoride. Fluoride is not a very good nucleophile because it hydrogen bonds. Fluoride can hydrogen bond with water and product solvents and things like that. So what you can do is you can add a crown ether. The crown ether has a bunch of oxygen atoms in here, and there's structures in your textbook. Okay. And it sequesters the potassium ion. So now you have a fluoride ion that's considered naked. Okay, there's no ions or anything solvating that, and it can be quite reactive. And you can do this in a nonpolar solvent like, gasoline or something, okay? And that will get you the product, okay? Sometimes these are carried out in biphasic reaction mixtures. So sometimes you have 2 phases. Down here you have water, you have potassium fluoride, and then you have this crown ether that's used as a phase transfer catalyst. And up here in your organic phase is where the reaction occurs, okay? Your crown ether would be up here. And since the crown ether complexes, say, sodium ion or lithium ion, depending on the crown ether, and that'll bring it, because it's organic, it'll bring it into the organic phase, and it will cause the counter ion, like fluoride, to come up with it into the organic phase. Generally speaking, there's no way to dissolve potassium fluoride in organic hydrocarbon solvents because the fluoride and potassium ion are ionic. They're just so polar, they're not going to dissolve in gasoline. So it's a way for you to dissolve ionic substances in a very nonpolar solvent. Anyways, that's all I wanted to mention about crown ether in case your professor mentions that a couple times.